Okay, so it's time. So let us get started. Shares. Well, let me first ask the following question because I was kind of worried. So it looked like the attendance was a little low on Wednesday, and I was wondering if some of you lost power. So can you actually cast a poll on this? I just wanted to know. So far, nobody. Okay, we're in the middle of a poll. If you just joined, I'm asking you whether you lost power on Wednesday. Okay, so far none of you, but we also have only 12, actually, 9 students right now. So it's quite possible that there's a bias sample. That those of you who didn't have any problems, don't have a problem today either. That's why you are here. Those who did may are still having problem and they are not here. So I don't know what that means actually. So I'm still concerned, especially now that the attendance today also seems to be low. But I will have to get started anyway. So this is a really problematic situation. But anyway, so let's get started with the quantum field theory. And the first thing I do is just to recap what we have done in last lecture on Wednesday. So in order to see the meaning of the Schrödinger field theory, as opposed to Schrödinger equation in quantum mechanics, we introduced interactions. The first thing we did is to put all the particles in some kind of potential well. So in this case, all you had to do in the field theory side is to add this term to the Lagrangian minus potential energy as a function of position and psi dag of psi. And one thing I don't think I said on Wednesday is that the meaning of this term is fairly simple, right? Because psi dag of psi is the analog of A dagger A in harmonic oscillator. It just counts the number of particles, but at position X, meaning that that's the number density of the particle at position X. So what this term does is for per number density at a particular position, which experiences potential energy V of X, you are adding it over the entire space. So that's the meaning of this additional term. So it has a very clear meaning of it. And even together with this new term in the Lagrangian, if you derive the Euler-Lagrange equation from this Lagrangian, you still get something that looks like the one particle Schrödinger equation. So we still haven't broken this coincidence between the Euler-Lagrange equation from field theory versus Schrödinger equation in quantum mechanics. But this does get broken once you introduce the self-interaction among particles. So we first did that on the lattice so that we know what we are supposed to do. And it turns out the term you're supposed to add is this one here. And now this one has a new feature, namely that this is not linear in A, not linear in A dagger, or more specifically, not bilinear in A and A dagger. This is a quadratic term, which has 2 powers of creation operators and 2 powers of annihilation operators. So this term looks quite different from what we used to have. And indeed, this actually tells us a clear difference between field theory and quantum mechanics. So by taking the continuum limit, which we have done already a couple of times by now, you are supposed to keep this product of the energy for the interaction U times this lattice constant D, and this product is kept fixed as I send lattice constant to 0. And then at the end of the day, I find this Lagrangian. And this Lagrangian, because we had this quartic term in A and A dagger, also end up being quartic in field. It has 4 powers. And when you derive the Euler-Lagrange equation out of this Lagrangian, this is what you get. And now, this is definitely different from the Schrödinger equation in quantum mechanics. Schrödinger equation had to be linear differential equation in psi so that we can have superposition principle. If you have psi 1 as a solution to the Schrödinger equation, and if you had psi 2 as a solution to the Schrödinger equation, you can talk about linear superposition between the two, still being the solution to the Schrödinger equation. But if the equation is nonlinear like this, that's not true anymore. There's no superposition principle. So this equation we get from this field theory Lagrangian is not Schrödinger equation. This is some other field equation or wave equation, which we haven't seen before. So this is the point where we clearly see this idea of second quantization is a wrong idea. This is not Schrödinger equation. And we have now Lagrangian that doesn't lead to Schrödinger equation, but nonetheless, we are quantizing it to get the multi-particle quantum mechanics now with this self-interaction among particles in it. So this is where we'd like to sort of sum up on what we discussed in terms of quantum mechanics and quantum field theory. And so let me finish up the next slide and to talk about this. So what we learned and was just talked about is that we now have this Lagrangian, which we quantize to get the multi-particle quantum mechanics with self-interaction among each other. This Lagrangian at the classical level leads to this wave equation. It's an Euler-Lagrange equation coming from this Lagrangian. And this wave equation is not a quantum mechanical Schrödinger equation. And when we quantize this wave equation, then we have this canonical quantization condition between psi and psi dagger, being annihilation operator at position x, creation operator at the position y. So that's the way we derive this commutation relation from this first term in the Lagrangian. And we know that this is not Schrödinger equation because it's non-linear. So I said this already, because the equation is non-linear, if you have one solution, psi1, and if you have another solution, psi2, linear superposition of two solutions is not necessarily a solution to this wave equation. This wave equation doesn't satisfy the superposition principle. And we have many examples of wave equation in nature like that. If you have the fluid mechanics, Navier-Stokes equation is a nonlinear wave equation. So that's why it's very difficult to solve. And if you can come up with a new non-trivial solution to Navier-Stokes equation, that's a fluid mechanics equation, because it's nonlinear, that's already a mathematically incredible achievement. And you're welcome to try this because there's an institute called Clay, the Institute of Mathematical Sciences, which awards you $1 million for finding a new interesting solution to this equation. So whenever you have a nonlinear equation, that's always rather difficult to solve, which is very different from what we have seen in quantum mechanics class, solving Schrödinger equation. So now we have this nonlinear wave equation. We don't quite know what that is, but we quantize it, and that's something we have done already. And then you find particles out of this equation. And that's exactly the opposite from what we have done in quantum mechanics. So I mentioned this on the first day of class. QFT is in some sense the opposite from quantum mechanics, because in quantum mechanics, what you do would start with the idea of particles, and then you introduce canonical commutation relation between possession and momentum of this particle. And that would allow you to write down the wave equation. That's a Schrödinger equation. And in possession space, that's the Hamiltonian you have in classical mechanics, but you replace the momentum inside the Hamiltonian by this derivative operator because of this canonical commutation relation between x and p. And now you find a wave equation that describes the matter wave. So you start with particles and you get waves out. That's what you have done in quantum mechanics class. What we do here is the opposite of it. We have this nonlinear classical wave equation. And when you quantize this classical wave equation, you find particles. So that's what I meant. We are doing it in the opposite direction. And we can construct states with no particles in it. That's a vacuum state that is annihilated by all of the annihilation operators at all positions x. Then you start creating particles, one particle state, two particle state, and so on and so forth. So that is what we do in quantum field theory. So let me emphasize again, in quantum mechanics, you start with particles, and you get wave out. In quantum field theory, field is just a different name for a wave. And field is something that satisfies the wave equation like this. And by quantizing this wave, we find particles out, like the states I showed down here. So that's what I meant by going the opposite direction. From particle to wave is what quantum mechanics does. And in QFT, we go from wave to particles. So that's the opposite directions. But this is actually due to a limitation of our brain, I would say. So the language we have had grown out from our daily experience by interacting with the natural world and other human beings and animals and so on and so forth. So the language we have is based on our daily experience. And unfortunately, for most of us, our daily experience doesn't include quantum phenomena. Maybe some of you do. Maybe you are sort of next generation human being that you grew up with quantum physics. I don't know. But for most of us, that's true. So the language we use is limited by this experience that particle is a particle, is never a wave. A wave is a wave, and it's never a particle. So our brain is incapable of describing something that is a particle and a wave at the same time. That's why we have to do something like this. We take a starting point, being a particle, and we quantize it to get wave out so that you have a description that is simultaneously a particle and a wave. Or we can decide to start with a wave. That's the starting point now. We quantize it to get a particle out. Once again, we have the description that allows us to talk about what is a particle and wave at the same time. So we can take either of these starting points, but what we would like to do is somewhere in the middle always, because quantum physics itself is never purely particle or purely wave. We just take a different starting point, but still trying to describe the same thing. But it turns out taking wave as a starting point has an advantage, which I emphasized already. One, quantum statistic is built in for identical particles. And second, our Hilbert space, namely Fock space, includes states with different number of particles all at once, so that we are now capable of describing processes where a number of particles can go up and down, like emission of photon, absorption of photon. So let me emphasize just once last time, this is just a different way of starting a description of describing quantum physics in the middle. Rather than starting from particle first, we are starting from the wave first. And physics we describe is still identical, but our language now based on starting with the wave is in some sense a bigger language that we can do more things with it. And that's why we're studying quantum field theory. Okay, let me stop here and actually do a poll, I think. Oops, or maybe not. I thought there was a poll for this. Oh yeah, there it is. Okay, so let me do that. So I'd like to get your answer to the following question. So I emphasized that now we have this nonlinear wave equation. We are quantizing this nonlinear wave equation and trying to get the quantum physics out of it. But what does this wave equation represent? That's the question. So your first choice is that, well, this is actually not a classical wave equation because there's a h bar in it. And second choice is that, well, this wave equation doesn't mean anything. It is only meant to quantize, and so that we can get particles out of it. And third choice is that, well, this equation probably means something, some unusual state of matter. And fourth, it shows that Erwin Schrödinger went nuts. Okay. can see some of you having fun. All right. Okay, I think this is it. All right. So this is the poll result. So one of you, two of you said, this is actually in here in quantum because there's an H bar in it. And you're actually right, given that there's H bar in it, this still doesn't look like a classical field equation. And if you go to the lecture notes on Schrödinger field, what I did there is to first change the normalization of psi to absorb H bar into it, and also change the parameter m and lambda, and further absorb additional powers of H bar in it to make it actually turn into a completely classical wave equation that doesn't have H bar in it. So it turns out that I agree with you. This equation doesn't look a classical wave equation because there's H bar in it. You can actually fiddle with it to make it as a purely classical wave equation at the end of the day. So it turns out that there is some meaning to a wave equation. But what is it? I haven't told you yet. So second option, the four of you taken this option, that this is only meant to quantize, to obtain particles out of it. So far it looks like it, because that's the only thing I have explained to you. But I hope to come back to you next week to talk about actually a physical phenomenon, which is described by a classical limit of this wave equation. That turns out to be Bose-Einstein condensate of cold atoms. So it turns out that the choice 3 actually does have a merit because it does represent some unusual state of matter where you are supposed to really absorb this H bar into various definitions of parameters. So in some sense, 1, 2, 3, 4 options are all correct. And we will come back and talk about that kind of a weird system, which is described by this nonlinear wave equation, which sort of looks like Schrödinger equation, but it's not because it's nonlinear. So we'll come back and talk about that. And finally, it shows Erwin Schrödinger went nuts. I don't know about him. So I don't think he actually knew about this very well, but Erwin Schrödinger himself actually debated a lot with himself and also with the community what his wave equation actually meant. And of course, in the end, now we learn that it's meant to be a probability wave with a superposition principle and everything. But when Schrödinger first wrote it, that wasn't quite clear to him. And it was Max Born that came up with this interpretation as a probability wave after Schrödinger. So Schrödinger himself actually didn't quite know. And he was always fascinated with this idea that this is kind of wave in space-time, which is exactly what we are talking about now in the context of quantum field theory. So I doubt he went nuts, but he actually didn't know. And what we do in QFT is in some sense what he wanted to see all along. So that's the historical context to it. And so let me stop sharing now. And so now you're witnessing this interesting historical development. The quantum mechanics wave equation was invented by Schrödinger first, but he himself wasn't quite sure. Now, in some sense, we are seeing what he wanted to see. So that's where we are. Okay, let me stop here and I welcome any questions. And as I said a couple of times already, this conceptual shift is probably the most difficult part of this course. But once you go over this hump and get used to this idea of quantized field, then everything becomes a lot easier from this point on. So please fire up with any questions you might have.
Is it just a coincidence that the Euler-Lagrange equation for certain cases is identical to the Schrödinger equation?
Yeah, that's an excellent question. And I try to actually answer this question later on. So it turns out that the reason why it looks so similar is because it's sort of forced upon us by a symmetry of the system, namely a Galilean invariance. So let me come back and talk about this later. So hold on with this question for now. But thank you for asking that question anyway. That's an excellent question I anticipated. Any other questions?
Yes. So far, we've been able to create and annihilate particles at specific positions. So I was wondering how the uncertainty principle plays into this.
Yeah, that's an excellent question too. So what we're going to do probably next Wednesday is to go to momentum space. So you can also introduce creation annihilation operators of particle of definite momentum instead of definite position. And then we can start going back and forth between position space and momentum space, not in quantum mechanics now, but in quantum field theory. And that's when we can start talking about the uncertainty principle between position and momentum. So again, I can't answer this question today, but we'll come back and talk about that. Excellent question once again. Anything else?
Wait, so are all these Fock space states position eigenstates right now?
So far, yeah. But as I said,
Okay.
we can do this in momentum eigenstates too. And you will see that next Wednesday. Thank you.
Thank you.
Okay, so let me move on. So now we'd like to switch the gear in the following way. So as you saw, we started with harmonic oscillator, and then we made a jump of using harmonic oscillator as a creation annihilation operator or particle at a definite position. And we sort of build up quantum field theory by paying careful attention to the fact that it needs to reproduce quantum mechanics we knew and loved. So that was a bottom-up approach. So I wanted you to sort of, in some sense, experience how you might have discovered quantum field theory on your own. But now that we have this Lagrangian, we would like to see if this Lagrangian makes sense, namely that we now do top-down. So given that we have this Lagrangian we came up with, we start all over again to see whether we really get what we wanted to get. So once we have a Lagrangian, we have this well-defined procedure, right? You first identify the time derivative of the coordinate in the Lagrangian. Then you define the canonically conjugate momentum out of it. So conjugate momentum is IH bar psi dagger, given this term. And you first set up this commutation relation. Now, this commutation relation is not something we started with in the analogy to harmonic oscillator. This commutation relation is now we derive from this Lagrangian. So that's what I mean by top-down. This is given, we start everything from this Lagrangian. So the first thing we get with this canonical commutation relation. And second thing we get is the Hamiltonian. So Hamiltonian is PQ dot minus L. PQ dot cancels this first term. The rest remains with the minus sign because it's PQ dot minus L. And hence we have now this Hamiltonian. So again, this Hamiltonian is now derived from this Lagrangian. So that's another step in top-down. And using this canonical commutation relation, we can define what we call the vacuum state to start building up the Fock space. The definition of the vacuum state is the state annihilated by the annihilation operator at every position x. So that's the vacuum state. And on top of this vacuum state, we start to build one particle state, two particle state, three particle state, and so on and so forth. That's the Fock space. And in general state, then, is given by linear superposition of all these states we have constructed. For a given n number of particles, this is the generic state of n particles at positions x1 to xn. And in general, we consider linear superposition of those states weighted by this function capital psi. So this is the way we can write arbitrary state which has n particles in it. And the way we know that this is indeed n particle state is because we can define this number operator. And again, based on the analogy to harmonic oscillator, where the number operator is A dagger A, creation operator times annihilation operator, it's the same here, creation operator times annihilation operator, but summed over all positions x. Namely that psi dagger psi gives you number density at position x. And when you integrate over x, you get the total number in the entire space. So what we would like to do is go one by one. First, look at the one particle state and define this general superposition of one particle state. We verify that it's indeed one particle state by acting number operator on it, and then derive the equation which this coefficient function capital psi needs to satisfy. So this is what I mean by top down. We now have a Lagrangian. We do everything starting from this Lagrangian and derive out of the Lagrangian. And there's no ambiguity in what we are doing. Once you specify Lagrangian, everything comes out of it. So that's the top-down approach in QFT. So let me pause here and see if there are any questions about what we are doing.
Professor, I was just wondering how the canonical commutation relation falls out of the Lagrangian.
Yeah. So remember the definition of the canonical conjugate momentum. So if you think of psi being Q, what we're looking for is P, right? And P is the derivative of Lagrangian with respect to Q dot, and that's this psi dot. So this whole thing in front, IH bar psi dagger, is meant to be P. So canonical quantization condition is QP is IH bar. Q is psi of X. P is IH bar psi dagger, so IH bar H dagger, so IH bar is missing here. And QP is IH bar. The one thing that's different from the particle mechanics you have seen is that X or Q came with in discrete fashion. You may have Q1, Q2, Q3. 1, 2, 3 is a discrete label. But in field theory, psi or Q has a continuous label as a function of position in space. So instead of having Kronecker delta here, I need to put delta function. And in 1D, this is delta function in one-dimensional space. When you go to 3D, of course, there's delta function in three-dimensional space. So psi of X and IH bar psi dagger of Y has a commutator given by IH bar times delta function. That's the definition. Then I cancel the IH bar from both sides, and that's how I get this canonical commutation relation out from this Lagrangian. Does that answer your question?
Yes, thank you.
Okay, great. Any further questions on this page?
How do we get the Hamiltonian? So when we do what P times Q dot minus the Lagrangian, does that P in that first term have to be under an integral as well? Because
that's right. Right. So again, if you remember particle mechanics, Hamiltonian is PQ dot minus L. But when you have multiple Q's, you have to sum over PI QI dot, summed over I minus L. And this sum is now replaced by this integral over X. So PQ dot summed over indices is exactly the first term in the Lagrangian. So when you take PQ dot minus L in the field theory now, the PQ dot is precisely the first term, so that's canceled. And the rest is just the negative of the Lagrangian, and that's this Hamiltonian over here. I hope that makes sense.
Yeah.
Okay. Any further questions here? All right. So let me first get started with the first the one particle state, and that's what you're working on in a homework problem. So this is now the number operator. We now have this state, psi dagger, acting on the vacuum. So let's verify that that's one particle state. So n acts on this state. N is now given by this operator. And to avoid the clash of notation, I changed the dummy variable to y, so that number operator is dy, psi dagger over y, psi of y, acting on this state, psi dagger of x, on vacuum. And here we play this trick again. So when you interchange the order between psi of y and psi dagger of x, psi of y acting directly on the vacuum state vanishes by its definition, namely that vacuum state is supposed to be annihilated by annihilation operators at every position y. So if I change this psi of y, psi dagger of x to this commutator of psi of y and psi dagger x, difference between the two is the opposite ordering of negative psi dagger of x, psi of y, now acting on the vacuum state. Then you see the psi of y acts directly on the vacuum state, so that gives you a vanishing contribution. So going from the first line to second line, I have not changed anything. But then we know that what this commutator is from the canonical quantization condition. This is nothing but the delta function. And now that this is a delta function, I can perform y integral by replacing y by x everywhere, namely that this is now psi dag of x. So number operator acting on this state turned out to be the state itself times 1. So that's how you see that this state psi dag of x acting on vacuum is indeed a one particle state. And now that we know this is a one particle state, we define this general superposition of the one particle state given by this integral. So we weight this one particle state created specifically at position x by some function, capital psi, taking linear superposition over the entire space in x. So this would be a completely general way of representing whatever state you like, which has one particle in it. So what you would like to do on the next slide is what you've been doing a homework problem, namely that knowing the Hamiltonian, you can work out time evolution equation of this function capital psi for a generic one particle state. Let me pause here again. Are there any questions about this? Okay, there doesn't seem to be any questions. All right, so now we would like to work out the time evolution equation of this capital psi. So this Schrödinger equation, and I flashed this slide on Wednesday, but I realized I went very fast there. So what we like to do is write out this Schrödinger equation. And Schrödinger equation itself doesn't depend on whether it's a quantum mechanics or quantum field theory or what representation you take. That's really gold equation in whatever system you have. Time evolution of a state is given by the Hamiltonian. Hamiltonian is a time evolution operator. Hamiltonian is what gives you the infinitesimal change in time, which corresponds to translation in time. And that's what we learned from Emily Noether a long time ago, namely that every conservation law in physics comes from a symmetry of the system. And in this case, symmetry to move forward in time. Time translation is a symmetry of the system. And hence, there's a conserved quantity called Hamiltonian, or energy as its eigenvalue. And the Hamiltonian then generates moving time forward in translation, and hence this equation. So this equation remains unchanged, whether you're talking about quantum mechanics or quantum field theory. You can even do classical mechanics and write down Poisson, a Hamiltonian equation of motion using Hamiltonian. So either classical or quantum, either field or particles, Hamiltonian is always what moves the time forward. So that's why we stick to this equation. And now that we stick to this equation, we work out the left-hand side of the equation and right-hand side of the equation for the generic one particle states we talked about on the previous slide. Left-hand side of the equation is given by this. So this is the state we defined. The only thing that depends on time is this function here. So we take the derivative of it, and that's this left-hand side of the equation. So left-hand side of the equation here is given by taking time derivative of this function capital psi. Now we could work out the right-hand side of the equation using this Hamiltonian that was given to us from the Lagrangian. So what we do is to act this Hamiltonian on this one particle state. And once again, we rely on this canonical commutation relation, and we play the trick of replacing this product acting on the vacuum state by the commutation relation acting on the vacuum state, so that we can replace it by delta function. So the way it works here is this. starting from this vacuum state, I created one particle with the psi dagger. Then I annihilated it by psi, created again with psi dagger. So in all of these terms, I use the commutator of psi and psi dagger, psi and psi dagger, to let this delta function act on the vacuum state. And to make that simple, I did one trick, namely to rewrite the first term in the Hamiltonian. By integration by parts, I act this y derivative on psi dagger instead, with the negative signs here. Once again, I'm being a little sloppy about surface terms. You can put it in periodic boundary condition, or you can put it with the Gaussian wave packet. Either way, I allow myself to do this integration by parts. So I can rewrite this psi dagger by delta function. But I also have this additional term, which we learned from having self-interaction among particles. But at this level, this identically vanishes because I created only one particle here. So I go from 0 to 1. But then I have psi going from 1 to 0, and another psi going from 0 to nowhere. So this term gives you identically 0. So it turns out that the level of this one particle state, this term doesn't do anything. So I can forget about this. So I only focus on first two terms. And so that's what I said, though I can forget about this, the second term, because going up once, down once, and there is no way to go anywhere with a second annihilation operator. So this contribution identically vanishes. So all you get is the contribution from the first two terms, where I use this trick to rewrite this psi of y and psi dagger of x by this delta function. And I still have x integral and y integral in here. But now that I have this expression, I can go ahead and do y integral. Using delta function, I just substitute y everywhere by x. So I get this. And the only trick I played is this the derivative squared acting on psi dagger creation operator. And once again, I did integration by parts to let x derivative acting on psi dagger, now to let it act on this function capital psi. And because this is second order derivative, integration by parts give you minus sign twice, so it doesn't change the sign at the end of the day. So that's the end result by working out the right-hand side of this equation in the Schrödinger equation. Now we compare the left-hand side and right-hand side. Both right-hand side and left-hand side has this psi dagger acting on the vacuum. So that part is common. So what is supposed to compare then is what multiplies that one particle state. On the left-hand side, this is the time derivative of this function capital psi. On the right-hand side, I have this spatial derivative in potential acting on this function capital psi. So to make sure that this equation is satisfied, I need to equate these red parts on both sides of the equation. And now you see this is the one particle Schrödinger equation in potential V. So this is the way we now reproduce the one particle Schrödinger equation for this function capital psi by working out the Schrödinger equation very carefully and explicitly. So here you see this distinction that little psi we have in the Lagrangian is really not what satisfies the Schrödinger equation. Of course, we knew that because this equation was nonlinear. But now you see a different roles played by this little psi as an operator of creating and annihilating particles versus capital psi, that's just a number, it's not an operator, which satisfies the one particle quantum mechanical Schrödinger equation. So I hope this point is really the key point that will tell you how this little psi, which is an operator in quantum field theory, and capital psi, that represents the one particle wave function, going back to quantum mechanics, have different roles. They look similar in equation, but they have totally different meanings from each other. Okay, let me stop here and pause if any questions about this.
Yeah, I have a question.
Go ahead.
So I was just wondering, in the Lagrangian, there's like a term that is the time derivative of psi, but here we're assuming that d dt of psi dagger is 0. I don't understand like how, I don't know, how like psi has a non-zero time derivative, but psi dagger doesn't.
Thank you for asking that question. So that's the answer is that because we took Schrödinger picture. So when you remember what you did in quantum mechanics, when you wrote down the Schrödinger equation, all the time dependencies was in the ket. On the other hand, all the operators were assumed to be time independent. And so you could have done it the other way. If you take Heisenberg picture, states don't change as a function of time, but the operators do instead. So at the end of the day, what you want to make sure is that certain physical quantities, like expectation value of the operators, come out to be the same no matter what picture you take. So picture is something we pick for convenience. It's not physics, but physical quantities should come out no matter what the same way. So here we took Schrödinger picture so that the states have time dependencies, but the operators don't. And that's a choice. It turns out when you especially go to the relativistic quantum field theory, you really would like to treat time and space on an equal footing. And because the operator, field operator depends on space, you'd rather want the field operator to depend also on time. So the Heisenberg picture makes more sense once you go to relativistic quantum field theory. But for now, we are treating time differently because we are treating a only non-relativistic system so far. So we are free to choose whichever picture you like. And for the purpose of seeing the equivalence between quantum mechanics and quantum field theory, Schrödinger picture just turns out to be more convenient way to do it because we have this function psi, which captures all the dependencies on time without worrying about how operators evolve, so that all time dependencies are now captured in this function capital psi at the end of the day, which turns out to be equivalent to the Schrödinger equation in quantum mechanics. I hope that answers your question.
Yeah, thanks.
Okay, great. And that's an excellent question. Any further questions here?
Yeah, I guess sort of like a follow-up.
Go ahead, Anna.
Then, so like, I mean, in the previous slides, when we've found the Euler-Lagrange equation for our kind of little size, the operators. So that's the opposite choice then, that the operators evolve, and then in that case, our states would not evolve, or?
Okay, let me see if I can go back there. Sorry, that would take a while. Sorry about that. Maybe I should actually go further back, it seems. I think what you're talking about is this slide here, right? So I have this Lagrangian, and this is Euler-Lagrange equation. And indeed, Euler-Lagrange equation is an equation for the variable you have in your system, which has time derivative in it. So Euler-Lagrange equation turns out to be always an equation of the operators in the Heisenberg picture. And that was true in quantum mechanics too. So if you write down the equation for Q operator, or position operator, momentum operator, those equations are equivalent to Hamilton equation of motion in classical mechanics. And in quantum mechanics, the Heisenberg equation of motion is that IH bar of the time derivative of some operator is given by the commutator of that operator with the Hamiltonian. And that requires the operator to be in the Heisenberg picture. So Anna, you're right. So whenever you see Euler-Lagrange equation derived from the Lagrangian, at the quantum level, you need to say in addition that, well, we are writing this down in Heisenberg picture, not in Schrödinger picture. Does that answer your question, Anna?
Yeah, thanks.
Okay, great. So we have now seen the equivalence. And so that, let me go to the next slide. And the next slide is this two particle state. Oh, just hold on. I think I wanted to ask one question here too. Yeah, that's okay. And the two particle state is, again, we define by acting this creation operator twice on the vacuum state. And we verify that indeed has an eigenstate of this number operator. So the idea is that when you act this number operator on this state here, you first commute this psi with this psi dagger. That gives you 1. Then further commute this psi of x with psi dagger. That gives you second 1. And they add up to give you eigenvalue 2. And I don't think that's so surprising to you because you have done this already in the case of a harmonic oscillator when you act number operator A dagger A on the two particle state or the state 2 where you have the ground state with 2 powers of creation operator acting on it, then n has eigenvalue 2 on that state. So this is actually exactly the same algebra. And I'm afraid I have a typo here. This vertical bar should not be there. Otherwise, it should be correct. Sorry about that. So, and again, general two particle state would be a linear superposition of the state where we created two particles at the positions x1 and x2. So we define this linear superposition. So this is the state we created in a Fock space. You create particles at position x1 and x2. Then I take linear superposition of that state and integrate over x1, x2 with this weight function capital psi. And as you know already, this capital psi ends up having the physical meaning of the wave function of a two particle state in quantum mechanics. And one thing we learned here already is that the identical particle business is built into this. Because first of all, I can interchange the order of two psi daggers because these are the two operators that commute. And so far, I haven't changed anything. Then, remembering that x1 and x2 are dummy variables of integrations, so I'm free to change the labels x1 and x2. So I consistently change x2 to x1. So this is now x1. Correspondingly, this x2 is now x1. And then change x1 to x2. So this x1 is also changed to x2. Integrating over x1, x2, it doesn't matter in which order you do. So this one remains the same. So now I found this. Then I compare the first line and third line where the arguments, two arguments of this capital psi are now interchanged. And I haven't changed anything, so they are supposed to be the same. So namely, I have this capital psi, which is symmetric under the interchange of two arguments, x1 and x2. So I kept saying this, and I'm repeating this once again, but now I'm doing top-down approach. I want to make sure that this symmetry under interchange of particles really does come out automatically, starting from the given Lagrangian and just start building the states out of that Lagrangian. Okay, any questions about this? The next slide is again time evolution.
How are you able to switch the capital psi arguments? I get the operators themselves because they commute, but as for capital psi, how are we?
Yeah, from here to there, I just relabeled x1 by x2, x2 by x1. So if this was confusing, I could have done it the following steps. First, I decide to call dummy variable x1 as y2. So this dx1 is dy2. This psi dagger of x1 is now psi dagger of y2. And then this x1 is y2 here. And same here, this x2, I call this now y1. So this is dy1, this is y1. Then after doing so, I switch back to x. So I relabel y1 by x1, y2 by x2. Then I end up with this one over here. So I did not switch two arguments. All I did is to change the names of the dummy variables or integral. But at the end of the changes of dummy variables or integral, I end up with an expression which just turns out to be the switch of two arguments. And that's the argument I made over here. Does that answer your question?
Yeah, thanks.
Okay, great. Any further questions here? So I'm just verifying what I have been advertising all along. Starting from the QFT Lagrangian, we are deriving now everything top down. And the symmetry under the interchange of particles does come out as a consequence. I'm not imposing anything. This is the consequence of starting with that Lagrangian. Okay, so now we look at time evolution. Again, the Schrödinger equation is the gold standard equation for everything, QFT or quantum mechanics, even classical systems I mentioned. So we use this equation now applied to a generic two-body state we introduced with the same Hamiltonian. So once again, the left-hand side of the equation is just given by the time derivative of this coefficient function capital psi. The tricky thing is now we need to act this Hamiltonian operator on this state. And it's a little long here, I apologize. But what we do here is just, again, purely straightforward. I have this Hamiltonian as an operator. I act this operator on this state we define for two particles in it, as we verified on the previous slide. So what we have to do is to make sure that we commute this psi operator in the Hamiltonian and psi dagger operator in the state carefully. But now we'll see a new feature here, namely that I have created two particles out of ground state. So out of this vacuum state, out of this vacuum state, this psi dagger would bring it up to one particle. This psi dagger would bring it up to two particles. Then with this last term in Hamiltonian, I can go from 2 to 1, 1 to 0, now back to 1, back to 2. So this second term doesn't vanish this time. I have to include it in my algebra. So that's the piece I need to do carefully. So I don't repeat doing the commutator of working out psi and psi dagger here. So the first commutation gives you psi dagger of x2, while the commutator gives you delta function between y and x1. And doing commutator the second time, I get delta function between y and x2 instead, leaving psi dagger of x1 left over. So these are the two pieces you get. And I'm writing down these first two terms of the Hamiltonian. So this part looks similar to what we have done with the one particle state. But now comes a new contribution. So I need to let this psi and this psi, both of them commuting with psi and psi dagger, so that at the end of the day, both psis act on the ground, on the vacuum state and give you identically 0. So I end up now having two commutators. These two psis, both at y, with a commutator with the psi dagger of x1 and psi dagger of x2. And if you do this carefully, you find two possibilities of doing commutator of this psi with psi dagger of x1 and that psi of y with psi dagger of x2, or the first psi of y with psi dagger of x2 instead, and second psi of y with psi dagger of x1. So I get a factor of 2 from that. And that factor of 2 cancels this factor of a half. So I have now little lambda over here. And now that we have two commutators, I have two delta functions. And I do the same thing again. I do the integration by parts so that this y derivative act on this function capital psi. But now I have to remember the y may be either x1 if I choose this term here, so that y derivative would be x1 derivatives, or if I choose this delta function here, y derivative would end up being x2 derivatives. So I get these two contributions. So this derivative term here ends up being either second derivative in x1 or second derivative in x2. I have both of these contributions. For this potential energy term, you just integrate over y. So this v of y is substituted either by x1 or x2. So I have these terms of the potential energies at position x1 and x2. Now the last term is an interesting one. I integrate over both. I integrate over y, so that the y as an argument of psi dagger is now replaced by x1. But not only that, this y is also replaced by x1. So I end up with lambda delta x1 minus x2, multiplying this coefficient function capital psi. And then the end result is, again, I compare this one here and this one over here. So left-hand side of the equation and right-hand side of the equation need to agree with the same stuff up front. So they have to be the same. Now you see, this is indeed the Schrödinger equation for two particles, with the kinetic energy for first particle, kinetic energy for the second particle, potential energy for the first particle, potential energy for the second particle. But now you see these two particles interact with the short-range interaction given by this delta function. So this is no longer a free particle. That's what we wanted anyway. But again, we are not going back and forth and trying to build things up. Given the Lagrangian, that just comes out of it. Namely that this QFT just contains automatically a wave function for two particles, which include kinetic term, potential energy term, and the delta function interaction between the two particles. Again, everything is top down. Once you're given the Lagrangian, this just comes out to be the equation as an arbitrary linear superposition of two particle states that needs to satisfy this equation, which turns out to be the two-particle Schrödinger equation. So two-particle quantum mechanics is now something you can derive out of this Lagrangian of QFT. Okay, let me stop here again and pause for questions. No questions? Okay, if everything is clear, let me move forward. Oh yeah, and this is where I wanted to do a poll. So the way you can derive these Schrödinger equations for the wave functions in quantum mechanics out of the Schrödinger equation in quantum field theory is the homework you're doing right now for the one particle state. And I'm actually a little late. It took more time to get through this the discussion on Wednesday, which I hope to actually come to this stage, but I didn't. So I should pose this question. So if you are struggling with the homework right now, simply because we haven't actually finished this discussion on Wednesday, then you might want to have extra time. So let me ask this question, whether you would like to have an extension of the deadline of homework number 2 to Monday morning. And if the answer is yes, please cast yes. But to make sure that everything keeps going, I will post a new homework 3 today, and that will be due next Friday. So even if I make an extension on the deadline, the next homework gets posted today. It's due in 1 week. So the homework 3 doesn't change, but only the homework 2 gets a little extra time over the weekend. Okay. All right, so let me close the poll here. So it's clear that some of you didn't have any problems getting the homework problems through and don't need extra time, but some of you, actually more of you do. So let me extend the deadline to Monday morning. For those of you who could do this anyway, you're welcome to submit it today, obviously, and submit the homework before the deadline. Of course, there's nothing wrong with that, and you're welcome to do so. But for those of you who struggled, because I haven't actually gone to this stage in the lectures on Wednesday, you would like to have extra time, you're welcome to do so. But beware, it doesn't give us extra time for homework 3. So you have this overlapping period of weekend where you are facing both homework 2 and 3. But at least that, I hope, is helpful to you. And homework 3 actually turns out to be extend this analysis to 3-body state. And it's a little bit more algebra, but you will repeat the same thing. So in some sense, you can work on them simultaneously starting today. So I hope that doesn't cause any problem for you. Okay, so I will do that. And Reggie, please take note of the extension. I try to change this deadline on the B courses as well. All right, so this is how you get the two-particle Schrödinger equation for the wave function in quantum mechanics. Now it's derived from quantum field theory. So what we did till yesterday, to Wednesday, is to start from the quantum mechanics and build up QFT. Now what we're doing is that once you're given QFT Lagrangian, you can derive multi-particle quantum mechanics with no additional inputs. It's already all built into it. Okay, so now we do this for 3-particle state. That will be the next homework problem. So we first verify that indeed this state where you act 3 creation operators on the vacuum state indeed has eigenvalue 3. The way you show it is exactly the same again as the harmonic oscillator in quantum mechanics. N is A dagger A. You have 3 A daggers in it, and that ends up giving you the eigenvalue 3. So that's something you can work it out very easily. And once again, a general 3-particle state will be a linear superposition of this specific 3-particle state where particles occupy position x1, x2, and x3. So linear superposition is taken with this arbitrary coefficient function, capital psi. And this is what you would do in your next homework problem. You work out the Schrödinger equation by comparing the left-hand side of the equation, where time derivative acts only on this function capital psi, to the right-hand side of the equation, where you need to work out the Hamiltonian operator acting on this general state. And here's the Hamiltonian once again. And this is the answer you're supposed to get, namely that time derivative of this coefficient function capital psi is given by this, which you would work out from acting this operator on this state on the right-hand side of this equation. And once again, this is indeed exactly the Schrödinger equation you would expect for the wave function for 3-particle state. Namely, I have sum over the kinetic energies of 3 particles, sum of the potential energies of 3 particles. But in addition, I have interactions among them, again, given by this little lambda times delta function, for all 3 combinations among 3 particles. This is the interaction between particle 1 and 2. This is the interaction between particle 1 and 3. This is the interaction between particle 2 and 3. And in addition, just by following through what we have discussed before, you can interchange x1, x2, and x3 among the creation operators because they commute. And once again, because x1, x2, x3 are dummy variables of integration, you can relabel them. And that way you can show that this coefficient function capital psi is symmetric under interchange among any combination of these 3 particles. So this is how you derive 3-body wave function of quantum mechanics, which is automatically symmetric under interchange of 3 particles. And this wave function satisfies the familiar Schrödinger equation with the familiar Hamiltonian for 3 particles, now even with interactions built in among them. So once again, we are verifying this point that once you are given QFT Lagrangian, n-body quantum mechanics just follows from it. You don't need additional input. It's already built in. And quantum statistics for identical particles is built in. And you can derive Schrödinger equation for arbitrary n-particle state from the fundamental principle of your QFT. Let me stop here again if there are any questions. Is everything clear? Okay, so you can make it even more general. So this is the arbitrary n-particle state. And then you can also make the interaction among particles, which the question some of you asked on Wednesday, I believe, not from delta function now to something more generic. So if the particles have long-range interaction, like the Coulomb potential, then you will put in the interaction potential, which is given by two positions. So in the case of a Coulomb potential, this will be E squared over the distance between Y1 and Y2. And the general interaction term then can be written this way. And I will give you in a second what it means. So this is a generalization of it. So when you take this interaction potential between two particles to be a delta function, lambda of delta y minus 1 y2, in that case, you can perform y2 integral right away. So you recover what we used to have, namely that psi dag up, psi dag up, psi at same positions y, 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 y. So this form is the generalization of the delta function potential we had on previous slides. But now you can use this for generic long-range potential for the interactions among particles, like Coulomb potential. And you define n-particle state. Once again, I act creation operators for n particles on the vacuum state. So this is the state where particles occupy specific positions x1 dot 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 xn. And then I take a linear superposition of them to represent arbitrary n-particle state you are interested in by this coefficient function capital psi. And you write down the Schrödinger equation for this state. And left-hand side of the Schrödinger equation is time derivative of this state, where time derivative acts on t for this coefficient function capital psi that's here. And when Hamiltonian acts on this state, you use this canonical commutation relation many times over to rewrite it. And at the end of the day, this is what you would get. So I have this coefficient function capital psi. I have this one differential operator acting on that represent the kinetic energy of each particle. I have n of them. Here I have external potential. So now that I have both interaction potential and external potential common to all particles, I put X subscript to it. And this external potential appears again for every particle, summed over n particles. And then for each pair of these particles, I have this interaction going on between the two positions of them. So this is the generic n-body wave function and Schrödinger equation for it you would expect in quantum mechanics, which is now derived from the quantum field theory. So n-particle Schrödinger equation in external potential Vx and the interaction among them through interaction term V int is what was derived now from QFT. So this is the demonstration that QFT is exactly equivalent to multi-particle quantum mechanics. But in addition to being multi-particle quantum mechanics, there's this built-in automatic symmetrization under the interchange of particles. And unlike quantum mechanics, where you need to first specify how many particles you have in your system to write down wave function, you didn't have to do this. In QFT, you have this huge Fock space, which contains states with arbitrary number of particles in it. So QFT contains all of these Schrödinger wave equations for arbitrary number of particles n without specifying it. So that's what you get from QFT. Repeat it again. QFT is exactly equivalent to multi-particle quantum mechanics, which you have seen in quantum mechanics class. But you have two new ingredients, automatic symmetrization for identical bosons, and big Fock space, where you can talk about states with arbitrary number of particles. And that's why you can talk about creation and annihilation particles. You can go up and down. And you can even talk about states with huge number of particles in it, like Avogadro number of it, like what we see in macroscopic system, in condensed matter physics, atomic physics, because you don't need to write the states with 6 times 10 to 23 arguments in it. So that's how QFT ends up being very useful in talking about multi-body systems in quantum physics. Let me pause here again. Are there any questions about this? Is everything okay? Are you hearing me? Are you okay? This is the problem with Zoom lectures. I would never know. Okay, I see a thumbs up, so that's all right. Okay, I'm just keep repeating the same thing over again. So now you're getting sort of sick of what I'm saying to you now. Let me just give you that there's an intuitive reason why the interaction term looks like this. So this is meant to be interaction between particles at position x and y, right? So what's going on in this term is this. So if I write this psi dagger, psi dagger, psi pop, psi in a slightly different way, I move this psi dagger to this side so that I have psi dagger of y2, psi of y2. So let's say that's actually x. So I have psi dagger of psi over here. And the rest is psi dagger y1, psi y1. So that's this psi dagger of psi of 1, y. So what's going on here is that this is the product of two number densities at position x and y. And so I have this many particles per volume at position x. I have this many particles at position y. They interact by this interaction energy, V int. And then this blob of the unit volume, you are supposed to sum over every place in space. So that's this integral. So this interaction Hamiltonian actually makes sense because it's just given by interaction energy given by certain number of particles at position x and certain number of particles at position y integrated over all positions. So even though this form of the Hamiltonian, I chose carefully with this particular ordering of annihilation operators and creation operators so that you can really derive this at the end of the day. But classically, this is just given as an interaction energy of certain sort of continuous distribution of particles given by number densities at positions x and y. So I hope this is now intuitive and that it makes sense to be part of the Hamiltonian. But now that we are talking about quantum physics, where we have to be careful about the ordering between psi and psi dagger, this is a specific way I wrote the Hamiltonian. But at the classical level, this is just the integral of the number densities of the interacting particles over entire space. So I hope that gives you a better intuition on why I had to actually write down this term in, at the end of the day. Okay, good. So here's another poll coming up. And I forgot what poll I was supposed to do. This is the question. So now I have shown you the equivalence between the QFT and multi-particle quantum mechanics. And this is, you can choose any of these options you like. It's not just a single choice. You can choose as many you like. And just I'd like to have your sort of feedback on where things are. So maybe you are now completely happy. Well, but you complain. We still don't know what this wave psi actually is. Why do we have to choose this particular form, the Lagrangian? We seem to have made it up to achieve what we wanted. So now that you're talking about top-down, is there any reason behind this? Well, we still haven't seen a photon. Well, we haven't dealt with fermions either. Okay, I'm still waiting. Okay, so let me close the poll. And one thing is loud and clear. None of you are happy. Okay, so that's something I learned. And specifically, you want to know about all of these things. So what is this wave? Psi. And as I said, I hope to come back to this question next week. It turns out that this psi is actually a classical wave, which turns out to be a collective behavior of large number of atoms, like thousands of them, behaving together as if it obeys the classical wave equation. So we will talk about what this wave actually represents. The next question is something I'd like to address in the next couple of slides. Why this particular form of Lagrangian? It came out of the blue. Why do you have to choose this Lagrangian? And certainly I agree we haven't talked about photon yet, and that would come up later in several weeks, not right away, but I promise that. And the last one, fermions, I'll come back and talk about on Wednesday. Okay, thank you for your poll. So that's where things are. So you are still unhappy on a couple of things. Why does Euler-Lagrange equation for QFT look like single particle Schrödinger equation? So far, the answer I have given you is that, well, I started with the QFT Lagrangian and that led to something that looks similar to single particle Schrödinger equation. So specifically, Euler-Lagrange equation, now with this new long-range interaction, looks like this. Euler-Lagrange equation includes actually extra integral, which I forgot to write, dy in here. And that's the way equation looks like. This is nonlinear. It's not Schrödinger equation. It's still distinct, but at least the first part looks similar. Where does the similarity come from? Why do you have to take this particular Lagrangian for QFT? Answering this question is actually a little technical, and I warn you, but it's because of the Galilean invariance of mechanics. So you all know this, Galilean relativity. So, SpaceX Dragon was a huge excitement for many of us. Just imagine that two dragons are passing with each other. And when you ask the question, okay, which one is actually moving? You all know from classical mechanics class, that's a stupid question to ask. The only thing that matters is relative velocity between the two, because there's no idea called absolute motion. It's all relative. And you can choose whatever that's moving constant speed as your frame of reference. And every inertial frame of reference, namely the frame of reference that are moving at constant speed with each other, are equivalent. You can just do this coordinate transformation that x now goes to x prime, which is given by x minus vt. That's the Galilean boost, going from one reference frame to another reference frame. And laws of physics doesn't change under this. So that is the Galilean relativity. And we have to make sure that the quantum field theory we came up with is invariant under the switch from one reference frame to another reference frame. It turns out that this requirement actually forces us to take this particular Lagrangian. Any questions about this concept of Galilean relativity? I bet you have seen this many times in classical mechanics. Is everything okay? All right. So it turns out that to implement this Galilean relativity into Lagrangian is a little complicated, because the transformation property of the field psi from one reference frame to another reference frame is not just you change this coordinate of x going to x minus vt, but on top of it, you need to change the phase of the field. And to understand why this is the right transformation property requires some mathematics. And I just put up a new revised version of the Schrödinger.pdf on B courses where I try to explain it. And in the first part, I just give you a bottom line, a quick story I call it in the lecture note. The rest is meant to be the derivation of why we have to take this. But for now, bear with me. This is the transformation we have to do. And when you write the Lagrangian with this transformation property, it makes sense that most terms look like psi dagger psi, because then this phase factor cancels between psi dagger and psi. So everything that's written as a function of psi dagger psi is invariant, because you can then choose the integration variable and do a shift integration variable to make sure that x minus vt is now an x integral again, and Lagrangian doesn't change. But the tricky thing is the term that involves derivatives, because this phase would also affect derivatives. To make sure that derivatives come in a very particular fashion between time derivative and space derivative, so that derivative of psi would transform to derivative of psi in the new coordinate with this overall phase factor. If this is the case, then taking derivative with the specific combination acting on psi, and again, you have an equal number of psi and psi dagger, so that this phase factor cancels between them, then your Lagrangian is indeed invariant. And that's exactly what we did in the Lagrangian so far. So the reason why you have to choose this specific combination of time and space derivatives is required by the invariance of the theory under the Galilean translation, Galilean boost, because of this additional phase factor. So the modern view of QFT is the following. You first specify symmetry of the system as Galilean translation invariance, Galilean relativity. You introduce fields that transform under symmetries. I've shown you transformation property of the field under Galilean boost. And in mathematics, this is the property called representations of symmetries or Lie groups of a certain symmetries. Then you write down the most general Lagrangian invariant under the symmetries, and that's what we did on the previous slide. And for each term you wrote, which is invariant on its own, you specify coefficient of each term. And those coefficients turned out to have physical meanings like the mass and potential and energy and so on and so forth. And once you have the Lagrangian, you quantize it. And then you get your quantum theory. And this is the modern view of QFT. The top-down view of QFT is this. Symmetry is first, fields next. Write down the most general terms you're allowed to write, specify coefficients, and quantize. And that's how you receive and derive quantum mechanics from top-down approach. So I'll stop here again, and I pose for any questions you might have. And this is basically the end of the class today. Any questions?
Can you sort of explain what's the last quantize mean?
Yeah, quantize means that when you write down the Lagrangian down to this level, it's not clear whether you're doing classical or quantum. And you can even say you're doing classical mechanics so far because you're just writing down these functions of psi and psi dagger to build up the Lagrangian. So up to the point 4, whether you're classical or quantum, it doesn't matter. You're doing the same thing. But the very last step is definitely different between classical and quantum because psi and psi dagger all of a sudden become operators of creating and annihilating particles instead of a classical wave. So down to point 4, that's completely common between classical field theory and quantum field theory. But the last step where you regard psi and psi dagger to be operators is when you quantize the system. Does that answer your question?
Okay, so it just means interpret the terms in Lagrangian as operators.
That's right.
Okay, thank you.
Any further questions?
Professor, can you go back to the previous slide? Yeah, so I'm wondering if the second D operator under the section of covariant derivative, is the second D operator a D prime that acts on X prime and T prime?
That's an excellent question. So you can say this is D prime too. But it turns out that the derivative with respect to T, there's no Jacobian because T and T prime are the same. And with respect to X, again, there's no Jacobian because X is just shifted by a number, so it's the same. So it turns out that D prime and D are the same. And thank you for asking the question.
In principle,
in principle, it could have been different.
Okay.
Yeah, that's right.
I see.
But for the Galilean boost, it turns out to be the same. So you have to be careful, for example, when you talk about spatial rotation, then X and X prime are related by certain angles. And there's a Jacobian associated with it, and you have to use the chain rule. So in that case, D and D prime can be different. So I sort of jumped ahead and used the fact that for Galilean boost, they are the same and didn't put prime on it. But you're completely right, Ryan. You have to be careful about that. For general symmetries, you might see in the quantum field theory. Thank you for asking the question.
Okay, thank you. And I certainly, sorry, I just suddenly come up with another. You said if you transform under rotation, is that also a Galilean transformation?
Yeah, so what we collectively call Euclidean symmetry or Euclidean motion is that you have spatial translation and Galilean boost at the same time, and spatial rotation as well. So that's sort of the non-relativistic analog of the Lorentz invariance
Okay.
and space and time translation and Lorentz boost at the same time. So this is, in the case of Lorentz symmetry, it's called the Poincare symmetry, which includes both full Lorentz symmetry and the space-time translation. In a non-relativistic case, that breaks down to spatial rotation, time translation, Galilean boost, and spatial and the time. Space translation, time translation, and space rotation and Galilean boost. So collection of four symmetries are the entire symmetry of Euclidean space.
Okay, I see. Thank you.
Any further questions?
Yeah, I just want to ask, what are we, I guess, solving for exactly? Would we solve for the field operator psi using Euler-Lagrange equations, or would we construct the Hamiltonian from the Lagrangian and solve for the wave function capital psi?
Yeah, so you actually would do with both in the end. So when you actually look at this Euler-Lagrange equation, then if you're looking at the classical theory, Euler-Lagrange equation is all you care. So you would like to solve this nonlinear equation, which is in general hard to do, but sometimes you can do it. And then we can see what kind of wave it would describe. So that's what you would do with Euler-Lagrange equation. In quantum theory, because you have this freedom of choosing the picture, you can do either way. You can solve this operator nonlinear equation and keep the states not changing over time. Or you can solve for the multiparticle Schrödinger equation for this coefficient function psi and keep this operator psi unchanged as a function of time. Either way, you're supposed to get the same physics out of it.
I see. Okay. Thanks.
Okay, great. Any further questions? Okay, so as I said, I promise you to give this extra time for homework number 2. Homework number 3 gets posted later today, and that's due next Friday. And I really hope you stay safe and have a good weekend. Bye for now.
Thank you.
Thanks.
Okay, bye.